Alright, today we tackle angled projectile problems, things that have a general launch angle that aren't necessarily running horizontally off a cliff. Tossed at some arbitrary angle, a ball has a velocity history that looks like the figure to the right, over here. Note that the constant downward acceleration bends the trajectory into a parabola. We again see the parabola that we've seen so many times with constant acceleration. Here, though, it's a physical parabola, right? It's not just that on a position plot it looks like a parabola. Here, the actual trajectory is a parabola through space. We see that because remember that the acceleration points along delta v. So if we take two particular moments, here's our original, and we have that delta v is, of course, v2 minus v1, which is v2 plus minus v1. And so we see we have v2 plus minus v1, and we end up with the acceleration downward, or at least we get delta v pointing downward, so the acceleration is downward. Or to put it a different way, the way that v2 has to go, it has to bend in this way so as to produce the acceleration that we know is towards the ground. The trajectory of a projectile will be determined by its velocity at launch, when we fire it. We'll decompose it into the x and y components, and usually the launch angle is given relative to the horizon, so Vix is associated with cosine theta, and Viy is associated with sine theta, but you should always check the problem you're in, because that isn't a physical necessity, it's just a convention. Right, we see here again, we launch at some angle. The velocity points along that angle. Of course, the object itself undergoes the parabola. It doesn't go straight along the initial velocity. It's bent downward by gravity. And then we break this into our usual triangles. The fact that there's now a vertical component of initial velocity complicates things, but not too badly. We'll need to turn the muzzle speed and launch angle into components of the initial velocity, so we use our we break down as we've been doing, that we have the horizontal is cosine, the vertical is sine, because we're measuring from the horizon. Let's illustrate this through a problem, kind of a typical problem. Ophelia kicks a soccer ball with a speed of 25 meters per second and an angle of 22 degrees from the ground. How many seconds is the ball in the air? And here we'll assume the ground is level, so it comes back to whatever height she kicked it at. We set up our constant acceleration equations. Here are the ones in x. Here are the ones, here's the one in x, and here's the one in y. Here's the velocity in x, here's the velocity in y. Starting at 0 and ending at some unknown time. Starting at 0 and ending at some known distance r, which was not asked for in our problem, but we'll still want it just to make sure we can use our equations fully. And then we have that it starts and ends at 0. We can also find her horizontal and vertical components of the initial velocity. And we know that there's no acceleration in the horizontal, so Vfx is going to be the same as Vix. We don't know Vfy yet. So we can use the constant acceleration equation that relates position to time squared, which is this one, yf equals yi plus viy delta t plus half ay delta t squared. And we can put in our particular values that Vf is 0 and Vi, right, we can do basically this. And if we look at this, we see that we can factor out, and this is the important bit, we can factor out a TF in that equation because we've got 1 power here and 2 powers here. So we end up with this equation here that either, right, we have 25 meters per second sine 22 degrees minus a half GTF, and all of that is times TF, and together they equal 0. But of course, if two numbers multiply 0, one of them must be 0. So either the thing that's highlighted in yellow there is 0, or TF is 0. TF being 0, that doesn't make any sense. The time of flight can't be 0 if the ball actually goes through the air. So it must be that the other factor is 0. So we just take our other factor, set it equals 0, solve over, bring the half GTF to one side, bring the 25 meters per second sine 22 to the other side, and then just do some algebra, and we get that the time of flight is 1.91 seconds. So that's how long the ball is in the air. Note that that boiled down to if I throw something straight up in the air with the with this initial velocity, how long is it in the air? It's the same problem because it's literally the same problem. The only difference, of course, that we in chapter 1 we would have specified 25 meters per second total. Now we've got to say, only the part of it that points upward. Of course, now it's easy to figure out how far it went as well. We go bax to the other position equation. We say xf is xi plus vix delta t. Remember, there's sort of a ghost 1/2 ax delta t squared but that is in fact 0 because AX is 0. So we plug in our values again, and we get that the range, XF is the range, XI was 0, VIX is 25 cos 22, and now we know delta T is 1.91 seconds, so we get the sort of ludicrously easy, the range is 44.3 meters. Is that reasonable for a soccer ball? Yeah, it's actually not too far off. It's a believable distance, although it's a pretty good kick. All right, consider the moment the ball is at its highest point. What can be said about its velocity, or about the components of its velocity at that moment? Remember, we're going to focus on at its highest point. At its highest point, the ball is no longer rising, but has not yet begun to fall. That's what makes it the highest point. If it were still rising, then it's not yet at its highest point. And if it's falling, it's coming from somewhere, so it's not also at its highest point. Therefore, the vertical component of the velocity must be 0, echoing things we had in chapter 2. But the ball is not at rest. It still has its horizontal velocity. All right, if it were at rest, then we would end up with this Looney Tunes case where it would go here and then accelerate downward and fall straight down. And obviously, not the case. All right, use the fact that the vertical component of the velocity is 0 to compute how many meters high the ball goes. Here we can set up our chart again. Right, xi is 0, xf is, well, we actually know what that is now. Yi is 0, yf is unknown, but we're looking for it. We know the two components. We know the final velocity. Now we know, right, that the vertical velocity is 0. Remember, this is now not, right, we're not at TF, but now we're at the time is what we would call the max height. And we start at 0. So we don't put in, for instance, we don't put an R here because we're not at that time. We're at the highest point. We don't know where we are yet, horizontally. The acceleration of the x is 0. The acceleration of the y is minus g. And then we say, well, I had to even pencil in here, we don't have the time, we don't want the time, so let's use the equation that does involve time. Our friend, the v squared equals vi squared plus 2a delta, in this case, y. So we say we end at 0, we start at 25 meters times sine 22, which we then have to square. Our acceleration is minus g, and our height is h. So we get that 2gh equals this thing squared. H is the thing squared over 2g, and if you run the numbers, apparently it's 4.47 meters. Is that reasonable? So about 12, well, maybe more, 15 feet. Yeah, that seems like a reasonable kick for a soccer ball. It might go about that high. So this is at least reasonable. You could also have solved the problem differently. It said use the velocity being 0, the vertical velocity being 0, but you could also have said, hey, the symmetry of the situation tells us that the time to maximum height is 1/2 the time of flight, and so we use that the time max height is 1/2 TF, where MH here, of course, is max height. 1/2 of the 1.91 seconds is 0.955 seconds. And then we can go back into the direct position equation and say y is its initial position plus VIY delta t plus 1/2 AY delta t square, or the height is 0 plus the vertical velocity times the time we just found plus 1/2 times minus g times the time squared, and not surprisingly, we get the same number. A little warning, sometimes you'll get a little bit off because you'll have rounded too much. So sometimes, if this come back as 4.48, I would not have really freaked out. It would have been a rounding probably at this stage. But in this case, it works out exactly the same, so good for that. And the symmetry can make it faster. I don't know if that's any easier than what we did, but it's a different way to approach it. And in kinematics, there's often multiple ways to do things. All right, this Desmos document plots the trajectory for any angle and speed. I'm going to run a video for you, so where it says change the value, we're really going to say just let it change and see what happens. And I'll plot complementary angles because that's the way it's rigged to do it in this demo. All right, so here we see all the things where we have things that add to 90, and that will tell us something interesting in a bit. Let's walk through it a couple of times. That's probably good enough. So what angle in degrees maximize the range of the projectile? Which made the projectile go furthest? All right, and we can see it happened at 45. Let's play again to watch it. I'll see if I can pause it at the right point. Almost. So at 45, it has maximum range. Why does 45 degrees give maximum range? Intuitively, there are two competing events. At a shallow angle, the projectile moves sideways very quickly, because Vix is large, but is not in the air for very long, because Viy is small. At a steep angle, the projectile has a lot of time in the air, because Viy is large, so it hangs a long time, but doesn't move very far over because Vix is small. The optimal angle will compromise between these two impulses, and 45 degrees has the components equal to each other. Rest assured that this can be proven, and in fact we will prove it next time.